Take a look around you. Everything, and I mean everything, from the chair you're sitting in to the screen you're watching right now to your own body, is made up of atoms. These tiny bundles of matter are the basic building blocks from everything, from molecules to moons, from seeds to solar systems, from gases to galaxies. For centuries, scientists were satisfied with stopping right here, the atom. They explained all matter, all the elements, by pointing to the atom. They made a model of the atom, put it in textbooks. Then it's like they placed it all into a black box and stuck it on a shelf. After all, the atom explained everything, right? That was it. But what if you could take a peek inside that black box? What if you could go deeper, farther than ever before? What if you could peek into the very core of the atom? Masquerade, the theory of everything, unlocks the tiniest secrets of the atom and the greatest mysteries of the universe. You will come to understand the minute details of the subatomic world. You're about to journey deep down into the time-warped frontier of the unknown. Our adventure starts here as we time travel back to the desert sands of ancient Egypt. Here, the contractors for the Great Pyramids pull together science, engineering, masonry, transportation, and construction in a way we haven't been able to duplicate in modern times. They were onto something about the theory of everything. Travel to Greece around 400 to 500 BC. Democritus, known as the laughing philosopher, proposed that everything is composed of atoms, and he was right. Fast forward to 1906, the English physicist J.J. Thomson won the Nobel Prize for discovering the electron. 31 years later, Westinghouse scientists in Pittsburgh built a 5 million volt Van de Graaff generator, the largest in the world. Their goal: smash the atoms into each other, break them apart, and see what would happen. They pulverized, pried, and probed until the atom came apart, revealing hidden particles: protons, neutrons, and electrons. The world of science was ecstatic. They finally isolated and named all of the elements and mass and matter. But it was a short celebration. Another bigger mystery appeared, something known as a quark. In 1964, two physicists, Murray Gell-Mann and George Zweig, independently proposed the idea of a subatomic particle, the quark. These fragments of smashed protons had all kinds of strange qualities. Yes, the quarks had quirks. They were up quarks and down quarks, top quarks, bottom quarks, charm quarks, and strange quarks. All of them had weird fractional charges. And the quarks didn't like to be alone. In fact, they died if left apart from other quarks. It turns out the proton requires 3 separate quarks. Not only that, but these quarks have to be available at the same time, in the same exact location to make one proton. 2 of the quarks must be up and down, and the charges of these 3 quarks have to add up to exactly +1 to create the charge of 1 proton. Yeah, it sounds pretty complicated, but there's a theory that pulls it all together and does it quite elegantly. It's called Masquerade, the theory of everything. For the most part, science makes good sense, but sometimes we make the most progress when we delve into what doesn't make sense. That's where Masquerade comes into play. It's a theory that not only explains the composition of all subatomic particles, but also gravity and black holes, light bending, time warping, and much, much more. Truly, this is the theory of everything. Let's dive in and discover more. First, why is Masquerade called the theory of everything? Because it ties a theory of elemental particles, gravity, and relativity into one end-all theory. Masquerade takes us inside the atom and explains everything about subatomic particles inside and how they're made and how they work. It started with this man, Clifford G. Arnell, a prodigious semiconductor engineer, inventor, and author. He was working on a multi-transistor integrated circuit back in 1967. And in 1969, Arnell helped design one of the world's first computer memory chips. In 1974, Arnell was standing in a hallway with a fellow engineer talking about electrons and anti-gravity when suddenly, poof, he got a flash of inspiration. In his mind's eye, he saw two single photons of light diving together and buzzing around each other in a form of a tiny ball. He knew at once he was looking at an electron. He was looking at an electron in a whole new way. Up to this time, it was thought an electron was as small as you could get. But the image Arnell saw pointed to two photons making up an electron. He was curious. What if you could pry open an electron and look inside? What if it really was made up of two photons like he saw? If this was true, it would revolutionize what we think about the atom. Arnell's curiosity became a lifelong passion. This is the heart of Masquerade, a whole new way of looking at the electron. Once you understand the basics of Masquerade, you can explain everything from neutrinos to nebulae. You know, we take a lot of life for granted. Take this apple. Usually we don't think about where it came from, or why it tastes like it does, or what it's made of. We just eat it. But a little curiosity can lead to great discoveries. That's exactly what happened to Arnell. Before we pry open an electron, there's something you need to know. No one has ever actually seen an electron. In fact, get ready. Electrons don't exist as a reality. They only exist as energy. Which brings us to the world's most famous equation from the world's most famous physicist, Dr. Albert Einstein. Yes, E equals mc squared. Energy equals mass times the speed of light squared. So what about this E? What kind of energy was Dr. Einstein talking about? The kind of energy that could blow up a city. And it all starts with tiny subatomic particles. Arnell took a closer look at Einstein's famous formula. He compared it to an older formula, Sir Isaac Newton's equation for kinetic energy, the energy of motion. Here's Newton's equation. Make your hand into a fist. Bang it into your palm. That kind of hurts because the energy that was in your moving fist is transferred to all those molecules in your palm. That's kinetic energy. This is the kind of energy Einstein was talking about in his equation. But wait, what does the speed of light squared have to do with energy? It's actually the speed of photons. To prove this, Arnell took Einstein's equation and did what he called a very simple mathematical trick. He multiplied it by 1. At first, that might sound like a duh, but actually, Arnell multiplied Einstein's equation by 2 over 2, which is equal to 1. Something intriguing happened. He got a new equation equal to the first, but in a new form. E equals 2 times 1/2 mc squared. In other words, energy is equal to 2 bundles of kinetic energy. The energy in Einstein's equation suddenly became clear. The 2 bundles of energy point to the 2 photons in the electron, just like Arnell pictured. So if your fist could go at the speed of light and plow into your palm, well, first, that would hurt a lot. But what kind of energy could split atoms into little pieces? And once you split atoms, you might release enough energy to flatten a city, or, as others feared, split the Earth in half. Whoa, whoa, whoa. Einstein feared both when he first published E equals mc squared. This is the energy that composes all matter. And by the way, mind-blowing statement coming up from Arnell. There is no mass. All we have is energy in a clever form that makes it act like a mass. That's why this theory is called Masquerade, because we have photons masquerading as massive elements of energy. So electrons as particles don't really exist, except as energy. And there is no mass, only energy. Things aren't always the way they seem. As Einstein put it, reality is merely an illusion, albeit a very persistent one. So how do we make sense of what we see, what we know about atoms? Masquerade points to the solution. In the simplest form, Masquerade says an electron is composed of 2 photons, but there's so much more to it. Using the theory, you can describe how an electron is constructed, explain the precise charge of all subatomic particles, predict the diameter of an electron, show why light bends around the sun, how you can warp time, and so much more. First, let's use Masquerade to see how an electron is built. Remember, Arnell's theory says there are 2 photons at play here. The Scottish scientist James Clerk Maxwell showed us that photons are electromagnetic particles of light. It's pure energy. Now, to make an electron, these photons have to be exactly the right frequency, and a very high frequency at that, 60 exahertz. So imagine this. We've got these photons racing in parallel at the speed of light from a distant star to Earth. Freeze frame. We've got a huge amount of energy here at an extremely high frequency. Something amazing is about to happen. We're about to see the very thing that made Einstein famous. It was May 29th, 1919. During a solar eclipse, 14 years before this, Einstein had predicted that light would bend around the sun. The length of this eclipse was 6 minutes and 51 seconds, one of the longest on record since 1416, and it allowed astronomers enough time to make very precise measurements. Scientists decided to put Einstein's theory to test. After taking careful measurements, they observed stars that appeared near the sun during its eclipse were not where they were supposed to be. Their position had shifted. This experiment proved Einstein correct. Light actually bends around the sun. So we've got these photons speeding along in a straight line. But as Einstein observed, the sun actually pulls them off their path a bit, causing them to curve. Now, what if we could magnify this curving effect? What if there was something with more gravitational mass than the sun? What if that something could actually bend the photons so much it could make them curve around in a circle? What is that something? Get ready. It's a black hole, and it's inside every electron. We normally think of a black hole as this mysterious, invisible entity in space with an incredibly dense ball of massiveness at its core. So massive, It can swallow light and gobble up planets like a cosmic vacuum cleaner. But this black hole is tucked inside every electron, inside every subatomic particle. Arnell's term for it is a massless black hole. Conventional thought says there's something called the Higgs boson that's responsible for all the mass in the universe. But what if it's a different story? What if in the center of every electron and every subatomic particle is a massless black hole? In that case, electrons would not need a Higgs boson to become massive. One way to picture a black hole is to look at a tornado. If you could capture a tornado and look inside it, you'd find out it's hollow and it's sucking things into it. Stephen Hawking and others imagined a huge object like a star that collapsed. So now that star is, say, the size of a basketball, but has the same number of massive elements packed very tightly within the ball. So it has the same gravity it had when it was a huge star. All that gravity is now concentrated so strongly that light will curl around it. The light goes into infinite circulation, trapped forever. Well, it turns out you don't have to start off with something as huge as a star or even a basketball. Masquerade shows us this can all happen on a subatomic level. For each electron, there are 2 photons curving around in a circle. Their circular flight path actually produces and maintains the massless black hole at its core. Let's do a quick comparison check. Let's compare the gravitational density of the electron, the mass per unit volume, to the sun. Here we find something remarkable. The tiny electron has a gravitational density 10 million times greater than the sun. So while the sun can bend the photon's path a tiny bit, the massless black hole inside an electron can bend the photon so much that they travel in a circle. In fact, under normal conditions, those photons will never escape. Here's one simple look at it. The stitching on this baseball actually shows the path a photon could take around the massless black hole. The photon curves continuously all the way around this thing until it gets back to where it started. Remember, there are actually 2 photons in every electron. Each photon is traveling around the massless black hole in exactly 180 degrees from each other in a very twisted, convoluted, and never-ending loop. An electron, by definition, has a charge of exactly -1. But where does it get this negative charge? Masquerade explains. It comes from the electromagnetic properties of the photons. When we first introduced the photon, we said a photon is electromagnetic. The word electro in the first half of the word tells us there's an electrical component to a photon. Each photon actually has an alternating charge of +1 and -1. But wait, the electron has an exact charge of -1. How does that work? Masquerade explains. It's something called the rotation of polarization. Picture each photon like a fighter jet. The fighter jet is on an extremely tight flight around the massless black hole. As it curves around, the fighter jet is also rolling. So we see first the left wing and then the right wing. Let's use colors to make it easier to see. Red for positive, blue for negative. Whichever wing is on the inside of its curve is always positive, or red. The outside wing, the wing we see, is always blue, or negative. So even though the photon is alternating charges between +1 and -1, all we see is the negative side. The photon rotates precisely in time with its travel, exactly 180 degrees for every 180 degrees of travel around the ball, or electron. So someone looking at the electron would only see one side of the photon in one charge, say -1 at any given moment. This is the rotation of polarization. Now, there's another particle that's exactly like the electron. It's called the positron. It's like the electron's twin sister, except the positron has exactly the opposite charge +1. To explain the positron's charge is as easy as falling off a log. All we have to do is the opposite. Go back to the fighter jet. In the positron, the wing exposed to the world is always positive. This is why Masquerade is such a wonderful tool. It explains negatively charged particle called the electron. And all you have to do is flip the photon's rotation and it becomes a positron. In fact, Masquerade explains the charged nature of all subatomic particles using rotation of polarization. That's the electro part of the electromagnetic. The magnetic on the last half of the word tells us there is also a magnetic component to the photon. So in every subatomic particle, you have these two kinds of energy, electric and magnetic. So we zoomed into the atom, then zoomed in further to the electron. Let's zoom in on the photon. Do we dare to zoom in even further? Why not? Let's explore what's inside a photon. Up to this point, there's been no real comprehensive model explaining the composition of the photon until now. Masquerade brings it into focus. Remember, the photon is the building block of all subatomic particles. It's a tiny electromagnetic bundle of pure energy. And yet, most everybody in the field of physics agrees that a photon has no mass. Wait, how can a photon exhibit an alternating electric charge, help create and maintain a massless black hole, and apparently possesses some kind of magnetic energy? How can it do all this when there's literally nothing to it? For our answer, we have to use our imagination and go back to Maxwell in 1862. He wrote, "We can scarcely avoid the inference that light, in other words, the photon, consists in transverse undulations of the same medium, which is the cause of electric and magnetic phenomena."
All photons exist as transverse pendulums traveling at light speed and producing energetic twists and torques in time which bear the electric and magnetic forces.
Transverse undulations. What was he talking about? Masquerade shows us. If we could stop a photon in its tracks, here's an idea of what we'd be looking at. Something like a ghost flying saucer. The diameter of the photon is fixed according to its frequency. The center of the photon is where alternating twists of time are producing to appear as the electric component of the photon. The diameter of the photon is where alternating rotations of time are produced to appear as the magnetic component of the photon. Now, let's take it for a spin. You can see the photon twisting on its vertical axis from red to blue to red to blue, going from negative to positive in its relentless travels. Back to the electron. Can we measure the diameter of an electron? Remarkably, using Masquerade, we can. How can this be done? Take a look at the stitching on this baseball. We already know the frequency of the photons are 60 exahertz. If we know the frequency, then we compute the wavelength of the two photons. This gives us a measure of distance on our electron ball. So, simple geometry, if you know the length of this path on the ball, we can also figure out the diameter of the ball. In other words, we can compute the diameter of the electron. Once we know the diameter of the electron, we also know the size of its twin sister, the positron. Okay, time to talk about a massive annihilation. If we set the stage so a negatively charged electron and a positively charged positron see each other, they will crash together and literally annihilate each other. All that tremendous energy we talked about escapes in the form of photons. And something more. Extensive testing and analysis has shown us that when an electron and a positron crash into each other, 4 photons are released. This is serious evidence for Masquerade, that each electron and positron is made up of 2 photons. Once these photons are knocked out of the electron, they're free from the massless black hole. There's a theory that any 2 of these photons could now recombine to become one double frequency photon. But Arnell's theory says something different. 2 photons may leave the scene, 180 degrees out of phase with each other. So they look like they're twice the frequency, but they never actually combine. In other words, Arnell says only 4 significant photons survive the annihilation. The rest is extraneous energy. So an electron and a positron collide. 4 photons are released. Experiments show a pair of these photons may find a remnant of a massless black hole that was left after the collision. It's possible for the 2 photons to reentangle, start curving around the massless black hole, and voila, a brand new electron or a brand new positron emerges from the crash site. This is not theory. It's actually been observed. When you think of gravity, what comes to mind? The gravity from the sun pulling on the Earth's gravity pulling on the moon? What if gravity is actually generated on a microscopic level? Masquerade shows it's not the sun itself that has gravity. It's the rotation of photons that give the sun or any massive body the appearance of a gravitational force. Yep, it all comes down to the curving motion of the photons. Think of a boat in water. As it curves around in a circle, the water inside the curve is compressed. The water outside the curve is decompressed. Now, you've got a picture of the photons in your head. As photons curve around in a circle, time inside the curve is compressed. Time outside the curve is decompressed. The result? The speed of light will be slower the closer you get to a gravitational object. The variation between the time density inside the curve and outside the curve is called a gravitational field. In Masquerade, gravity is called the gradient field. You can look at time compression by doing this. Let our palm be the sun. Out here in empty space, time is not as compressed. But the closer we get to the surface of the sun, time is more compressed. Let's shoot a photon through this field. The photon will actually go a little faster out of my fingertips than it does when it's closer to my palm. This is why light bends as it passes by the sun. It's believed that the space is curved. Actually, it's only time that is curved, produced as a time gradient field. Let's talk about warping time. Back in 1852, scientists believed photons required some kind of medium to travel. Just like water is required to make ocean waves, just like air is required to make sound waves, they proposed something called the ether. They believed this ether carried photon waves. They searched diligently for that ether. In fact, they searched for some 30 years. They scoured everywhere for it, outer space, inner space, but they never found it because it never existed. And yet Einstein predicted that a heavy gravitational object like the sun would bend the photon's path of travel as they passed near the sun. Einstein pointed to something outside the surface of the sun that was bending the light path. He indicated that something was a warp in time. Arnell put it this way: time is the missing ether. There's a way to detect a warp in time. Shoot a stream of photons through a given field and watch what happens. If the photons travel in a straight path, you can say nothing's affecting the photon's journey. But if the photons curve, there it is, a distortion of time. By the way, there's really no such thing as a straight line path for the photon, because space is filled with gravitational waves, which are actually warps in time. This gives a photon a very rough ride through space. Picture a boat traveling on a really choppy waves. If you could observe a photon for a couple of light years, you could see that photon bouncing and zigzagging until it finally arrives at Earth. Since the turn of the 21st century, scientists have been searching for something called dark matter, or a substance that's said to make up 85% of the universe and holding it all together. But what is dark matter? Masquerade provides an answer. Dark matter is nothing more than warps in time caused by gravitational objects. In fact, every distortion of time can be interpreted as dark matter. Einstein agreed there's no gravity as such. Instead, there are gravitational fields. Masquerade explains these fields only exist because of circulating photons within all massive objects. Here's a cool thing that happens. As soon as the photons bend in its path from a straight to a curve due to a gravitational wave, it actually reinforces that gravitational wave. Let's see how this plays out in a way you can see. The light you see from the sun doesn't get to the Earth until 8 minutes after it leaves. That means the sunlight you see now actually is a burst from the sun 8 minutes ago. So if the sun suddenly collapsed or was yanked out of the solar system, we would have no idea it happened until 8 minutes later. Gravitational fields also travel at the same speed of light, producing the same warping of time as photons bending through space. These traveling gravitational fields produce a very bumpy ride for photons passing through them. Going back to the boat picture, it's like riding across the top of a lake with choppy waves. When we talk about masquerade and subatomic particles, we can't forget about the quark. Let's take a look. At the center of every atom, you'll find at least one proton. Looking closer, scientists have discovered that the proton is made up of 3 quarks. Masquerade tells us that each quark is made up of 3 photons. Max Planck was a brilliant German physicist who won the Nobel Prize in 1918. He showed us that all photons are exactly the same, except for one thing: frequency. Frequency is the number of times the photon cycles its high-energy positive state to its high-energy negative state, and then back again in a period of 1 second. The electron charge is exact. So if each quark is made up of 3 photons, we can rightly expect the charge nature of the quark to be just as precise as the charge nature of the electron. The electron has a charge of exactly -1. Not minus and a little change, not a bit under -1, nope, exactly -1. When we look at quarks, we find out, sure enough, they also have a precise charge of either plus or minus 2/3 or plus or minus 1/3. Like we mentioned earlier, quarks don't like being alone. They like to be buddied up with other quarks. When you have 3 of them buddied up, 2 with a charge of plus 2/3 and 1 with a charge of minus 1/3, you've got yourself a proton. And the charge is +1. 2/3 plus 2/3 less 1/3 equals 1. Simple math, huh? The heart of masquerade is the photon. Think of the photon as the Lego brick of the atom. You can use it in different ways to build different subatomic particles. Change the exposed charge of the photons, and you'll get an electron, or a positron, or a neutrino. Change the number of photons from 2 to 3, and you've got yourself a quark. Keep on playing, and you'll come up with all kinds of combinations. You could make a quark that has all 3 photons exposing their same side to the world. So we'd have 3/3. This would make a quark with a charge of +1 or -1. It's not the norm for a quark, but there's no reason to assume it's not possible. To boil down Masquerade to its essence, we go back to 1974 and Arnell's flash of inspiration. It's two photons curving around a massless black hole to create an electron. Once we explain how an electron works, we can explain subatomic particles. To sum up, Masquerade makes it possible to explain all matter. So we took a look under the hood. What happens when we take this theory on the road? What happens when we apply it? What can we do? The answer: lots. First, a quick recap of Masquerade. 3 points. 1. Electrons are made up of two photons spinning around a massless black hole. This was Arnell's flash of inspiration, and it's verified by taking a fresh look at Einstein's famous energy equation. 2. There's no mass, only energy. That's the reason behind the name Masquerade. It's energy masquerading as mass. 3. As those spinning photons curve around in a circle, they produce gravity, and they compress time. So, this is the fun part. It's time to take Masquerade for a ride in our imagination. Masquerade creates a launch pad for ideas, which should be fun for physicists to play with. Fun effects such as anti-gravity. What if you could change the orbit of photons to make them stop experiencing the time gradient of gravity? That means an object, say a 100-ton locomotive, would no longer be affected by gravitational fields. And that means you could make it weightless. It's not that far-fetched. Scientists are already playing on the edge of this idea. There's even an account of it in the Bible. Some guys were cutting down a few trees. One of the workers lost an axe head. It flew off and dropped in the water. The prophet Elisha cut his stick, threw it in the water, and the iron axe head floated to the top. And then they fished it out. So, right there it is. In 2 Kings 6:6, an historical account of weightlessness. You might be able to shoot a laser into an atom in such a way that you reverse the polarity of one of those three photons, making up the quark, producing a strange type of new material. If you could energize one of those two photons in the electron, that photon might remember the event as one bit of digital memory, as explained by Masquerade. This could be the first step toward quantum computing. Masquerade also helps us see time in a whole new way. A mind-blowing thought: what if time is elastic? What if we could actually expand time, just like we can expand the surface of this balloon? The balloon doesn't get bigger by adding more molecules. We increase the space between the molecules. What if time could be stretched in the same way? This would produce a local speed of light that would be higher than the speed of light on Earth. Einstein already showed us time could be curved, bent, modified. When we pull time toward a gravitational object like the sun, we're actually compressing time. This has some exciting implications when it comes to space travel. Masquerade shows us that time is compressed closer to the sun. What if we go 2 times the distance the Earth is from the sun? Time might be stretched so photons can travel faster. We expect this time gap to keep growing. That means farther and farther we go into space, we could expect to see the speed of light exceed what we measure here on Earth. In fact, there's no reason to think that halfway between here and Alpha Centauri, the speed of light could increase by 10 to 15%. Keep going. What if time is actually much wider the farther out we go? At 20 light years, the speed of light might be traveling 10 times faster than we observe on Earth. What if the speed of light could actually get up to 100 or even 1,000 times faster when you get far above the plane of the Milky Way galaxy? If that's true, you could travel much faster than the speed of light. So something we thought to be billions of light years away might only be millions of light years away. So we don't have to go nearly as far as we thought. This strongly suggests that the universe is much smaller than anybody has calculated. So if the speed of light is not constant, how would a 10 times increase in the speed of light affect the age of the universe? We would end up with a universe much younger than we thought. These are all questions that beg to be explored thanks to Masquerade. Let's combine these ideas. If you had a way to become weightless, then acceleration to near light speeds would take less energy than a candle. When something becomes weightless, it's incredible what happens. Just think of a balloon full of air at the bottom of a swimming pool. What happens? The water pressure at the bottom of the pool is greater than one level up. There's more pressure on the bottom of the balloon than on the top. So the balloon goes up and keeps going up faster and faster using a minute amount of energy. What if we could apply the same principle to space travel? As we move away from the surface of the Earth, time is less compressed, like water near the top of the pool. So we can hop into our little spaceship and turn on our little gadget that works like the balloon in the swimming pool. We would float in the direction where time is less compressed. And space travel would be, well, it'd be simple. This is the fun and the wonder of Masquerade. It gets you thinking in a fresh, new direction. So if we've got particles with 2 photons, why not 3? Why not 4? What, 5, 6? You could create massive objects. What if there are other entire universes where everything is exactly the opposite polarity from what we have here? This is an age-old sci-fi idea, verified by Masquerade. So that's Masquerade, the theory of everything. It encourages you to take a peek inside the black box of the atom. Go deeper, farther than ever before. You may find yourself interested in how far you can take this in your research. You might be the one who produces weightlessness or anti-gravity. This is the beauty of Masquerade, the wonder of any scientific theory. It beckons you to step out, to launch into the unknown. Try it out, test it, see what you discover, and never stop exploring.